Alright, let's continue on through Chapter 6. Now, the remainder of Chapter 6 is kind of two things, some special factoring, as you can see here, and then 6.4, which is kind of leading us into the point of why we learned to factor in the first place. But first we learned the technique, and then we'll explain where it comes up later. Now, one thing to say early on in this next example is technically we can still do by grouping, but I'm going to show you what the answer is up above. Then we're going to work it out by grouping, and then we're going to show you kind of the rule here. So what by grouping would tell us to do is, since none of these can all reduce nicely, all right, since 4 and 28, they share a 4, but 49 doesn't, and 49 also is odd, so both of these are even numbers. This is an odd number. There's no common factor here, so we're still doing the, hey, why don't I multiply all these together? When I do that, I get 196. 196 comes from, well, 1 and 196. It comes from 2 and, what is that? I think 98. And then 3 doesn't work. 4 works, and we get 49, because of course that's where we got it from. But there's also 7 and, let's see here, what would that be? 196 divided by 7, 28. And there's also, let's see here, 8 won't work, just for sake of time, I'm pretty sure. 9 won't work, 10 won't work, 11 won't work, 12 won't work, 13 won't work, but guess what? 14 will work, and actually its other pair is 14. Now, this is part of the reason that it's a special product, but also remember, the main question from by grouping is, once I multiply those two, what are the factors of 196 that will add to 28? And the answer in this case is 14 and 14. Now that's kind of special. Let's see what works out there. We get a 14x and a 14x. They both need to be positive to recreate that sign that I see in the middle, plus my 49. And then I make my two groups, and then I play the same by grouping game. These share a, not 4x. These actually just share a 2x. And I'd be left with a 2x plus 7, right? Redistribute that, that goes back to 4x squared. Redistribute that, that goes back to 14x. Now, how do I make a match out of these? Well, they share a, looks like just positive 7, leaving me with a 2x plus 7. Now look at this, here's what's special. The 2x plus 7 in parentheses is now what's shared, so I bring it out front. And I put the remaining things on the outside together, which was a 2x and a plus 7. Now this is why we call it a perfect square or a special product, but here's the trick, how you can jump to your answer, and this is how we'll approach the rest of the problems. If you notice that your first term and your last term are perfect squares, then essentially what you should do is guess and check and verify through foiling that the answer is likely the rooted values on the left of each parentheses from the left-hand side, and the rooted values on the right in parentheses on the right-hand side. And so look at that. 4x squared comes from 2x and 2x. 49, another perfect square, comes from 7 and 7. Since 4x squared came from the left, we wrote both of those roots respectively on the left. Since 49 was on the right, we wrote its roots respectively on the right. We got the same thing, and it is my answer. So that's the idea, is that when you see a perfect square leading and a perfect square ending, don't even bother with the by grouping. Try this first. Jump right to these parentheses first, and then FOIL it out mentally or on the side and verify that it is actually the true solution. If it's not, then yeah, there might be some cases where this is a perfect square and this is a perfect square and this doesn't work, but I'm fairly confident in that. I think it has to work out this way, but I'm sure there's probably an exception somewhere. But it's kind of one of those things that as long as you're in this class introductory, intermediate algebra, then we should assume that behavior and then still verify it though, but we'll likely see it's true. Okay, so let's go through the rest of these pretty quickly then, because 16 looks like a perfect square. That comes from 4 and 4. And since it was h squared, I'll also use h and h. 81k squared also is a perfect square. It comes from 9 and k. And so now I'm going to assume that because I need to multiply to a positive and add to make a positive, then the sign in between is also positive. And now I'm going to verify that I do make my 72hk. Now I'm just going to say it verbally, but 4h times 4h is my 16h squared. Got it. 4h times 9k would be 36hk. And then 9k times 4h would be another 36. And guess what 36 plus 36 is? It is indeed 72, so we're good to go. Now, of course, you don't have to write these twice. You could, if you wanted to be a lazy mathematician, write it as 1 parentheses squared. And I'm going to write that down again just to remind us that when you see something like this and it wants you to expand it and go back to this, you need to write it twice so that you see the foiling process and you get those 4 terms that have a like term in the middle that combine to make your 72. All right, let's move on. This next one's a little interesting because I don't see a perfect square here. That's a 2. That's not a perfect square. That's a 50. So what's going on here? Well, don't forget that there's always the question of, is there a common factor? And if you look at 2, 20, and 50, well, there's actually a shared 2. And don't stop there. If you look at t cubed, t squared, and t, there's actually a shared t. If you look at u squared, and u squared, well, actually u squared comes out of everything. Let's see what we're left with now. We're left with t squared minus 10t plus 25. Now, inside my parentheses, this is actually a simpler factoring question. It's, just what multiplies to 25 and adds to 10, right? A is 1. I don't need to do by grouping. But I still want to call to your attention that even though this is something you would probably regularly factor, this inside parentheses is technically a leading perfect square. At the end, I've got a perfect square. So this is another case where we should probably, to save time, guess that it's the rooted values. Now this time they're going to multiply to make a positive, but combine to make a negative, so they both need to be negative. If you multiply 2 negatives, you will get a positive. If you combine 2 negatives, you'll get a negative. And guess what? Minus 5 and minus 5 do indeed combine to negative 10, and negative 5 times negative 5 does indeed combine to 25. Everything else works. This is our final answer. Awesome. All right, next one. Same thing. We've got a perfect square in front, perfect square in the back. Let's assume our solution and then FOIL it out and check. 64 comes from 8 and 8. Since they're going to multiply to be positive but combine to be negative, they should both be negative. And again, let's think now. Is it 9n squared? Yes, it is. That came from the rooted values. Now up next, the thing we need to really be careful about is 3n times negative 8 is negative 24. This is going to be a negative 24n. They're both going to be negative 24n's. Those indeed combine to make negative 48n. And there's my positive 64 at the end, so this is once again our answer. All right, so what we've learned so far is that, and this is a new way to approach your problem, is that you should likely assume or look for a leading perfect square and ending perfect square and assume this answer and try it out and see if it works. Okay, now then we get to differences of squares, and once again for the first example, well, I guess first to compare this to the last section, it is the same question. Do you have a perfect square on the left and a perfect square on the right, in the beginning and at the end? Yes, I do. Now what makes these ones awkward is where's the term in the middle? Well, once again, we could still answer this as a regular factoring question. There still is technically an ax squared plus bx plus c. It's just that this is gone. Well, why is that middle term gone? The short answer is conjugate pairs. Conjugate pairs will form your difference of squares. I think I wrote that in the notes online and posted it there, that we can write a little more here, but for now we're just going to move on from that. What I do want to do that we didn't do in class, though, is just remind you that you're still doing regular factoring. You're saying what multiplies to 25 and subtracts 2. Well, because I see nothing here, what multiplies to 25 and subtracts to 0? Why is there no middle term? Well, let's find out. There's 1 and 25, and there's 5 and 5. And guess what? 5 and 5 will subtract to 0. So that was the idea, is that, and I'm going to kind of cut to the answer, but because it was 5 and 5, and because I got a negative 25 at the end of my foiling, one of them is negative and one of them is positive, and these, again, by definition, are what we call conjugate pairs. It's the same two-term expression, but the sign in between is switched. When you have that, this is what happens from your foiling. You get your first from the FOIL, but your outer and your inner always cancel, so there's no middle term, and your last will make a negative perfect square, because that's what's going to happen every time in conjugate pairs. So with that being said, we can go through these next few examples really quick. The other way to go through this is again to say, hey, look, I see a perfect square and a perfect square. So I'm assuming it's going to be the rooted values, a and 11. One's positive, one's negative. Trust me, it works out, because here's the fun rhyme. Differences of squares, and that is a difference of squares. It's a square minus a square. That's what we mean by difference. Difference is another word for subtraction. So square minus square comes from conjugate pairs. Great, it rhymes. Okay, let's keep on going even faster. 4n and 3, 4n and 3. One's positive, one's negative. You should FOIL this out to see why, but again, the trick is if you see a leading perfect square and an ending perfect square, assume the solution will contain its rooted values and then verify afterwards. Whoops. Rooted values. Alright, so you can see once this rule clicks how quickly these examples go by. We're really just kind of referencing the homework here. Now this next one, this is a perfect square. Be careful, it's just that it was a squared. And of course 9 comes from 3 and 3. And there we go. So we're done there. Alright, and again we know we're done because even though this is a squared minus 3, 3 doesn't break down into nice square roots. Alright, let's look at this next one. I don't see a perfect square and I don't see a perfect square, but do you know what I do see? I see 2 even numbers. And look at that. There are your perfect squares that will turn into conjugate pairs. All right. Up next, I do see perfect squares. Now, there's multiple ways to go about this, but be careful. Although these are perfect squares, do you notice that at first they actually share a common 4? Now, what's interesting, and it seems like a coincidence, but it's not, is that when you're taking out that 4, which is itself a perfect square, you're left over with still perfect squares. So that's kind of interesting there. So now that we have that, let's see what we're left with. 10 minus 3v, 10 plus 3v. All right, there we go. So just be careful that you notice that first move there is that even though this is a perfect square minus a perfect square, and you might jump right to using 20 and what would that be? 20 and 6 and 20 and 6. Those would end up having common factors of 2 inside their parentheses, and I think we did it in the notes differently just to show it, but there we go. All right, up next, once again, I don't see perfect squares, so I'm going to realize that I can take out a 10 and a p. That would leave me with p squared minus 196. 196, you might not think it's a perfect square, but check it in your calculator. It actually comes from 14. And so we're done. Now, I'm saying we're done and I'm moving on, but trust me, what I am doing is I'm mentally refoiling it even as I'm writing the answer. Take your time to do that. Again, we are assuming that because I see a perfect square and a perfect square, that it is this form. But really, you want to refoil it in your head, and that also just helps you learn to foil faster when you need to. Okay, last one. I still see some common factors here. It looks like a 7 is shared and a b squared. Now, it might be hard to realize that 343 is divisible by 7, but more so the call out is, hey, if I just see a 7 and that's a really big number, why don't I just try to see if 7 goes into it? And hey, it does. Right? That's really what I'm doing there. It's just I know that that's 7 cubed because I've done math for a while. But even if you haven't done math for a while, what you should do is you should be suspicious if you see a 7 and some other very large number that's unfamiliar. You should kind of sit there and go, well, 7 really only has 1 and 7. I wonder if this has a 7 in it, and that'd be nice to take out. It probably will in the factoring section. Right? Not guaranteed, not always. But while we're in this topic, and you see one number, you might as well try to see if it divides into the other number if you're not sure. All right, now the other thing that's a little awkward about this one is it's kind of written out of order, right? The variables, and that happened a few times, the variables came second. That's fine. It's the same process. Where are your perfect squares? 49 is on the left, write its rooted values on the left. B squared was on the right, write its rooted values on the right. Just follow that pattern there. Where the perfect square is, write its rooted values in the same corresponding place, right? Perfect square on the left, rooted values on the left. Perfect square on the right, rooted values on the right. 1's minus, 1 plus, refoil it in your head, make sure the middle term does cancel, all of those things. And look at that, we're making progress, and my kid's right on my table. Up next, sum and difference of cubes. This is a formula that's pretty nasty. I'm not going to give you an exam question on it, but I will still ask it in your homework. Its formula looks like this. If you have a perfect cube plus or minus a perfect cube. In other words, we're writing two formulas at once here. We're being lazy mathematicians, and rather than writing almost the same thing twice, we're just going to say use one of these symbols, and if you start writing the top symbol, continue with the top line if there is one. And we end up with something like this. Now this formula is a little bit awkward to work through the first time you work through it, but hopefully you'll grow to see that it's not too bad. And again, if this wasn't going to be on your exam, this would probably be one of the harder ones to memorize because we don't use it that frequently. But when it shows up in some later classes, it's nice to see it. But honestly, it's so rare that it shows up that I just don't feel responsible to make you memorize it. But maybe you'll see it later and remember this moment. So how do we use this formula? Well, the first thing is we need to notice that I see a perfect cube and a perfect cube. One other thing that's interesting that we maybe need to call out is that there can be a sum of cubes or there can be a difference of cubes. Just to say, there is no such thing as a sum of squares, right? Of squares like we saw last time. There is no way to factor if it's n squared plus 25. The factoring sentence won't work, and hopefully I said that at least with the first two examples, that you can always say the factoring sentence with these, but it's nice to save time and essentially guess the answer and be right because we recognize that perfect square form. But you can always say the factoring sentence to go through these and get an answer. But the factoring sentence will not work for a sum of squares. It will not. But sum of cubes, whoops, flipped the wrong way. Sum of cubes, totally possible. So kind of interesting thing to call out there. Anyways, so how does this formula end up working? Let's go through a few examples. So we need to figure out how to find the cube root of something. There's a few ways of doing that. I guess on this calculator that I'm using, let me see here. I actually haven't used this calculator yet. Oh, there it is. See, there's this little literal, it looks like a square root, but there's a square on that square root, which means what type of root do you want to find? Well, I want to find the cube root. So I type it like that. I type the root that I want, the third root. I then type the second and whatever root I want button, essentially. And now I can type 125, and I get 5. So now I know that 125 comes from 5. Now d cubed obviously comes from d because it's literally d cubed. Now let's start dissecting what this formula is saying. It's saying if you notice a perfect cube minus a perfect cube, then the next thing you write, or the first thing about its formula, is the rooted values with the same sign in between, right? That's what it's kind of saying there. Find the rooted values, still put them on the left and right on their corresponding sides where they came from, and copy the symbol that you saw at the beginning. Now, obviously the formula doesn't read like that, but you need to be able to read it like that. I'm finding the rooted values, putting them in their corresponding positions, and keeping the sign I originally saw. That's what this is saying, but it's saying it with letters. Now from there, because you now have A completely isolated and B completely isolated, you can essentially form the right-hand side of this formula, or I guess the second parentheses on the right-hand side of this formula. Sorry, that was a mouthful, but we can form the second parentheses on the right by using the building blocks of knowing just what A is and just what B is. Let's see what I mean by that. A squared, or 5D times itself, is 25D 5d squared. All right. On the end, that's the next easiest one. There's always a plus sign, right? That's what that's saying. There's no choice here. There's no minus underneath. So it's always a plus sign, and it's whatever this rooted value is squared. So 2 squared is 4. Now the last thing to do is to put these together. 5d times 2, that's 10d. So I write 10d, but what symbol do I put in front? Well, let's read it now carefully. Minus is what I had, so minus went on the bottom. But now look, there's a plus sign on the bottom. So because I was using the bottom row, so to speak, of my choices, because mine started with a negative, I follow that through and use the symbol on the bottom, which is the copy, the negative. Now I follow through and use the symbol on the bottom, which now is a plus sign. All right, so you're finding the building blocks. You're finding singular A, so to speak, and singular B. And then you can square A, you can square B, you can put the two together, ignoring the sign, and then figure out what the sign should be based on the wording there. Now, the other way of saying it is, this one, I don't want to say it's the sign in the middle, but it kind of is, switches from the sign in the middle here is the only other way to say that. Okay, from there, once you make sense of that formula, but it can take a little bit of time, the rest of these should go by pretty quickly. The singular form of 64 as a cube root, not a square root, would be 4. If it was square rooted, it would be 8, but we're not trying to square root, we're trying to cube root. So cube root of 64 is 4. X cubed literally comes from x, and once again, 1 is indeed a perfect cube. It's a perfect fifth, it's a perfect seventh, it's a perfect 12th, it comes from 1. Initially, we copy the symbol. All right, let's keep on going. Square the first thing, that'll be 16x squared. Square the last thing, that'll be positive 1, it's positive regardless. Now, in the middle, 4x times 1 is 4x. And because there's a minus, I now write a plus. All right, I'm going to skip over this one. It's kind of too simplistic. Let's move on to this one. Once again, 64p to the 6th now. And this will be a little bit different. But 64 still comes from 4. But p to the 6th, think about it. Something was cubed to get you p to the 6th. And if you remember your rules, p squared was cubed because that's when they multiply together. So this time, again, to get a p to the 6th, you had to multiply p squared to itself 3 times over. So a squared is the thing that is your perfect cube root. Just let that sit with you until that makes sense. All right. Up next, now we're going to square this thing. So 4 times 4 is 16. But p squared times p squared is p to the 4th. A 1 is still a 1, and it still gets a plus sign no matter what. Now this time I multiply them both together. 1 times anything is itself. And because I wrote a plus sign, I write the opposite sign right here. All right. Maybe we'll do one more. Maybe we'll do this one. This one, I see a 4 and a 108. I think those share something. I also see an x to the 4th and an x. I think those share something. I think they share a 4x. So I'd be left with x cubed, and then 108 divided by 4 is 27. All right. So the 4x will tag along. The rooted values are x and, 3. So there's me finding out what this thing is cube rooted. Here's me finding out what this thing is cube rooted. Now let's deal with kind of the harder second half. Square this thing, x squared. Square this thing, positive 9. Multiply 3 and x. And because there's a plus sign here, put a minus sign here. All right, again, that'll only show up in your homework, but it's pretty nifty that we can break down sums and differences of cubes. Finally, and we're going to skip these questions for now, but what I want to show is kind of the order you should approach all these questions in. So the first thing you should do in every problem is look for a GCF. Then you should ask, is it a difference of squares? And then I would also ask, is it a sum of squares? Or sorry, is it a difference of squares, or do you think it's a perfect square? In other words, do you see a leading square and an ending square? Maybe assume your answer. Then think, well, are there cubes? Is it a leading cube and an ending cube? But notice the first thing there is factor out the GCF. From there, is it a by grouping problem? Do you have to multiply the first and the last? And then finally, is it just a regular factorable trinomial? In other words, you're almost going through this backwards, but just remembering that the first step is always, is it a by, or is there a GCF that I can take out before I approach any of them? All right. And really, I don't want to go over those 4 review questions. I think we'd be better off just going to 6.4. Because really, I guess maybe what these 4 are there to do, I just kind of have to say it, is they're there to kind of simulate what you'll expect on your exam. They'll just say factor, 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 factor. And it'll be up to you to diagnose what situation you're in. But again, we're not going to deal with perfect sums of cubes or differences of cubes. So a lot of these end up being that, just as a hint to you as you work through it. So I'm going to skip those for now. Let's instead move on to why we've learned to factor. So let's summarize everything we've learned and see what the relevance is. And the answer is this: 0 times anything is 0. So really, that's the zero factor theorem. Now, there's more to it, and you could look at the book or just Google zero factor theorem and get a much better answer. But hopefully, we'll just be able to see it by example in these first 2. We're trying to solve what makes this entire equation equal 0. Now, you'll kind of melt your brain if you just try to guess numbers and try them out. But really, the crux here is to look at these 2 and realize what's going on here. I have a parentheses times another parentheses. And so the thing is, you don't have to think about both of these at the same time. You can think about them individually, and you can say to yourself, if this first parentheses was to equal 0, then 0 times whatever this is, no matter what I plug in, would be 0 entirely. So what could I plug in to make this first parentheses 0? What makes this first parentheses 0? And I'm going to do this really quick, but you would just add 2 and divide 3. So n equals 2/3 will make this whole thing 0. And if you think about that, I mean, we should probably work that out at least once. 3 times 2/3 minus 2 times 4 times 2/3 plus 1. We're trying to figure out what that equals. Well, 3 times 2/3 actually is 2. You can use your calculator to verify that. Now, 4 times 2/3 is unfortunately 8/3. And then I still have the plus 1. Now, the thing is, and this is where we can sometimes get stumped or confused, is like, this is ugly and I don't want to figure out what it is. But the idea is, I don't need to figure out what this is, because 2 minus 2 is going to be 0. And 0 times whatever this ugly fraction is still 0. So I don't need to work out what the right-hand side is going to be, because if the left parentheses is 0, the right parentheses doesn't matter, because they're going to multiply and give me 0 no matter what. That's why we call it the zero factor theorem. If you've factored something down, then if it makes one factor 0, it makes the whole thing 0, because factors multiply together. Okay, but that means there's more than one answer to this, because what if the second parentheses was the one that was equal to 0? Well, then I would subtract 1 and divide 4 to isolate n, and I get negative 1/4. And so both of these are my answers, 2/3 and negative 1/4. All right. Now we'll explore what this means graphically for the sake of college algebra in a little, but for now let's just look at another basic example. This one's a little bit tricky because there's just a single x on the outside, but remember that x is technically multiplying or distributing to the second parentheses. Now we don't want to FOIL that out and undo it. We want to exploit that and say, oh, this is already factored out. Well, then what makes this first thing equal 0? And it's a little redundant because by writing it down, you actually solved it. 0 itself will make the whole thing 0. Now next, what makes 2x minus 9 equal 0? Well, add the 9 and divide the 2. I guess that'd be 4.5. So once again, there are 2 answers, 2 things that can make your entire question 0. All right. Now, the way we close this out, though, is by saying, well, what if things aren't factored out? And that's why we've learned how to factor in this whole chapter. right? Just to take us to this point. How can I solve equations where I see stuff like this? Here's how. Those two share a 3 and an x. Now that I've factored, I'm asking what makes 3x equal 0? Because if this first thing equals 0, it will distribute and cause the whole other side to be 0. What makes x plus 6 equal 0? Because if that equals 0, this 0 will distribute to whatever this is and get me 0. Now if I divide the 3, I get 0 itself. If I subtract the 6, I get negative 6. So those are my two answers. Up next, what if it's by grouping? Well, great, we learned how to do by grouping. 2 times 2 is 4. What are the factors of 4 that will add to 5? Well, there's 1 and 4 and 2 and 2. And again, it's adding because 2 times 2 is positive. That's why I'm writing the plus. Which one of those will add to 5? Well, the 1 and 4. So great, we still get to review by grouping one more time. There's a 1 with an x, a 4 with an x. That's how we're going to make 5x. They'll both need to be negative to truly make the negative 5x. And then we play our familiar by grouping game. What do these two share? They share an x. That's 2x minus 1. How do I make a match? Careful, it's a different question, but technically the same. We're still looking for the common factor, but we're really trying to make 2x minus 1. So negative 2 is the answer there. Negative 2, if I divide that out, will give me positive 2x. Negative 2, if I divide that out, will give me negative 1. I now have my matching set, which can be factored out, and I created parentheses for the leftovers. Now all that is still equal to 0. I was just factoring along the way. So I should have strung along the equal 0 every time, but for sake of time I didn't. But what makes each of these 0? Well, literally, you just write that down. What does make this 0? What makes this 0? And you solve, solve, solve. You get x equals 1/2. You get x equals 2. All right. Now, what I want to do is I want to show you what the graph of this looks like and show you the significance of what we've just found. So I'm going to write 2x squared minus 5x plus 2. And if I'm looking for where this equals 0, look what I find. That's another way of saying where are its x-intercepts. And I find the x-intercepts are at 0.5 and at positive 2. And take a look at what we found by factoring. We found that this whole thing equals 0 at 1/2 and positive 2. So by factoring, you are determining where a function will cross through the x-axis, which is going to be something pretty powerful for the rest of our math journey. Now the next one is actually a crazier interpretation, but first let's solve it and then look at the crazy interpretation. So the idea is we could subtract this 33k because at the end of the day, we only know how to solve things when they equal 0, right? That's what we kind of discussed at the beginning. This whole section is all about setting things equal to 0 and then factoring to be able to multiply to 0 because multiplying to 0 is easy. One of your multiples is 0. Okay, so let's factor this one. 3, 33, 72. Be careful, they actually share a common 3. That'll be k squared minus 11k plus something. Think about that. 72 divided by 3 is 24. All right. Finally, at the very end here, we're going to do quick factoring. What are the factors of 24 that add to 11? The answer is 8 and 3. So create your two parentheses. Because the number out front of my squared term is 1, I can jump right to the parentheses and I can think, how do I make negative 11 out of these two? Well, they're both negative. And will those two then multiply to a positive 24? They sure will. Then I know I found my answers. I found k equals 3 and k equals 8. Now, this is a super significant thing you've just done, and you probably don't realize it, and that's fine, but I'm just telling you this is where college algebra is going. Here's where college algebra is going. What you just did is you technically said, hey, I've got some quadratic. I'm going to write x squared instead of k, but I've got some quadratic which, if you want to put more terms on it, has been vertically stretched by 3, and its y-intercept is all the way up at 72. So first thing, practically, no one by hand is really going to graph a y-intercept at 72 with any real accuracy. Now from there, we're then graphing the line 33x or 33k, which means I'm graphing the line that does have a y-intercept of 0, but it has a slope of up 33, right 1, which once again, none of us are going to graph well. And what we've done, and we can zoom in on it here, is we've actually still narrowed in on where do these two graphs cross. And they cross at, and when I zoomed out, you can kind of see it, at x equals 3, and then I guess comma 99. But the point is, there's the 3 right there. See, the original problem wasn't set equal to 0. It was essentially saying, I've got these two functions, when will they cross? Which is what we did way back in chapter 4, but we only did that with lines. And if I keep on going here, should be another spot that shows up. Doesn't show up directly. Oh, there it is. And there it is at 8, 264. Now that's really crazy what you've done there. Again, it doesn't have to sit in about what we just said here, but you've said where does a really, really high up quadratic cross through a regular line? And the magic is, hopefully it didn't feel like you did that at all, right? You just said, I don't care if they're on other sides of the equation. I can move it over. I can find a common factor of 3. I can do some factoring, and I get 3 and 8 super, super easy. Now you could plug 3 back in, and you could plug 8 back in, and you'd see those other numbers, but really it's a super powerful technique, factoring, which is why I wanted to show that to you. Okay, we've got one last thing here, some projectile equations. And if you want to measure the height of an object after it's been propelled up, there's a formula you can use, which is going to be negative 16, I think it's 0.2, but we might just call it negative 16, I'm pretty sure for the simpler examples, t squared plus what we call VOT plus HO. Now, the idea here is, what do these numbers mean? What does the negative 16 mean? What does the VO and what does the H mean? The negative 16 is how fast gravity is pulling you down in technically feet per second squared. All right. Does that need to make sense? Not entirely, but just know that gravity, maybe this is the way of saying it, gravity is always there and gravity is never changing. So we're going to hard code it and we're just going to write what the gravity is in feet per second. It's negative 16. There's a little bit of rounding, but we're just going to not deal with decimals. So negative 16, that's gravity. It's always there. That's why it doesn't have a variable on it. Now, what are your variables? Well, VO is your initial velocity. How high up, or how, let me rephrase that. How much force are you applying upward when you throw the object? Or are you trying to make it go downward even faster and putting some negative pressure on it? Are you throwing it down or throwing it up? That's your VO. Your HO is where were you standing? So were you standing on top of a building? Were you just standing at like eye level? So you threw it up technically when you were like, I don't know, 5 or 6 feet off the ground because it technically left your hand higher than your head. So, technically your initial height shouldn't be 0. There's probably, again, 5, 6, 7 feet when you let go of the ball from where you were standing. Okay, so let's see what we can do with this equation. Just as an introductory kind of thing here. We'll see more questions about this later on, but it's nice to just expose ourselves to this formula as the last thing we do. All right, so it says the golf ball is hit from ground level. Now that makes sense because the golf ball is essentially on the ground. So we can fill some stuff in here. So gravity is still the same. I now know that this is going to be essentially a plus 0. And then it says it's hit with an initial velocity of 80 feet per second. All right, so 80. And there we go. Now it says after how many seconds will the ball hit the ground? Well, this is a funky way of writing it, but this equation is saying what is your height after a certain time. So this side over here will tell you your height, or in other words, this whole equation will tell you the height of the object after a certain time. So I want to know when that height will be 0. Okay, well, let's get to solving this. That'll be negative 16t squared plus 80t That'll equal 0. Now I'm essentially just chopping off the plus 0. From there, I'm going to factor this, and it looks like there's a common factor of actually negative 16 entirely and t. Just be careful that you identify that greatest common factor. I believe that would end up being minus 5. Let me double check that. 80 divided by 16. Yep, it's 5. Alright, so we've now just factored this. Remember, one of our factoring techniques was always take out a leading negative. If I solve both of these for 0, like we just learned how to do, this first one will just be, well, t equals 0, because you'll divide the 16 and nothing will happen. And then this one will be t equals 5. And at first that, I don't know, maybe it looks a little bit confusing. After how many seconds will the ball hit the ground? And my answers are 0 and 5. And that 0 might throw you off, but think about it. It says, literally, the golf ball starts at the ground level, so at time 0, before you hit it, it's still on the ground. That actually makes total sense. And evidently, after 5 seconds, that's when the ball will hit the ground. So that's your only true answer, but this one does make sense. Okay, now the next question is, how high will the ball be after 2 seconds? This is just using the equation in a different way. You're just actually doing this. You're just using 2 inside of the regular equation. And I'm still writing the plus 0, but that's fine. I'm going to work that out really quick. Negative 16 times 4, that's what you'll get when you square it, plus, I guess, 160, ends up being 96. So it's 96 feet in the air. And there we go. So just a little bit of a basic example of real-life application. You can use these quadratic equations to model a lot of things. Heights of object after time is one of them. With that, we've completed Chapter 6. I'll see you for Chapter 7.